Hello, good morning. Am I audible?
Yes, sir.
Okay, so today we start with new topic. Again, this will be a converters. Topic will be on the converters. It may be a DC to DC converter or AC to DC converter or DC to AC converter. Okay. And for this, we are having one special name, that is a resonant converters. Earlier to that, we have discussed PWM converters. That will be a first topic. That will be PWM rectifier and PWM inverter. And after that, we discuss the multi-level inverters, particularly medium voltage, high power applications. We have to go for multi-level inverter. Whenever output requirement of multi-level inverters, particularly for motors, induction motors, may be a 3 kV, 3.3 kV, or 6.6 kV. And for this, if you want to have variable speed, we require inverter. Under that medium voltage conditions, we require the inverter topology, that is the multi-level inverters. We have discussed three types of multi-level inverters: diode clamp multi-level inverter, or a neutral point clamped multi-level inverter. That is first topology. Second topology is flying capacitor multi-level inverter, and third is cascaded H bridge multi-level inverter. So today we start with this is a resonant converter. Again, it may be a DC to DC converter or a DC to AC converter, depending upon the applications. So we are in various type of resonant converters. So So here, various types of resonant converters. And if you see the word resonant is coming in this, means we require a resonance circuit is there. Or you can call as we are having a tank circuit. We are having a LC series circuit or maybe a LC parallel circuit that may be a forming the part of the converter. So here in this case, a particularly resonant word comes out. We require one LC circuit. It may be a series LC circuit or it may be a parallel LC circuit, and that will form the resonant. And where it forms the resonant, at which place it forms the resonance you can call it. And based on that, we are giving the names to this. So whenever across the load may be our part of resonant circuit. So our load is having a RLC load, and this RLC load may be a series RLC load or parallel RLC load, and that may be having a resonance. So here LC circuit may be a part of load, LC circuit, which will be we can call as a resonant circuit, and that may be forming the part of load. And whenever this resonant circuit is a part of load, that we can call as a resonant load converters. So we can say that LC circuit, which is a resonant circuit, undamped resonant circuit, that will be a part of forming the load. Okay, we are having a resistance load. At the same time, we are having LC, and that converter we can call as a resonant load. Another we are having this LC circuit, and the resonance may be formed across the switch. Switch means here semiconductor switch. We are using IGBT MOSFET. So LC circuit may form a resonance across the switch, and that we can call as a resonant switch converters. Whereas resonance we can particularly apply to a DC link. We have seen that we are having inverters. We have seen two-level inverter, three-level inverter, multi-level inverter in general, and we have seen that input to the inverter is given DC, and that DC link In case of VSI, we are having a capacitor. And so here, at this particular DC link, we can make a resonance of the DC link. DC link can make a to resonate. And whenever DC link make to resonate, that type of inverter, we are calling it as a resonant link inverters. And then we are having the high frequency integral half cycle converters, that will be another category. So these are the types of resonant converters. We are going in more detail afterwards, and after that we are finding applications of each of these converters. So this is our particular content of our particular this module. We have to discuss various resonant converters and their applications. Now, before going to that, we'll just revise the DC to DC converter. We have discussed in second year, particularly power electronics. We are having various types of DC to DC converters. And here we have shown a buck converter, DC to DC buck converter. If you look at the diagram, this is our input voltage. So our converter, DC to DC converter, we are getting the variable DC from the fixed DC. So our interest is we are having a fixed DC supply, and input of this DC to DC converter, buck converter, VD is the input voltage to the buck converter. We have shown this will be the switch, and our switch is either MOSFET or IGBT. And then we are having a particularly diode required for this. This is a filter circuit, LF and CF. We want our ripple in the output voltage should be very less. Output should be smooth and ripple free across the load, and for that we require a LC filter. So this is our DC to DC buck converter. The meaning of buck is output is less than input voltage. So we can vary the output voltage from 0 to the input voltage. So VO will be from 0 to VD, input voltage we are having. Now here we have to find out the expression for or we want to find out the relationship between the output voltage VO and the input voltage VD. We want to find out the relationship between output voltage is represented as VO and input voltage is represented as a VD. So what basis we can use? What is the basics we can use to find out the voltage relationship in case of DC to DC converters? What is the basic concept we can utilize to find out the relationship between output voltage and input voltage in case of a DC to DC buck converter, boost converter, buck boost converter, cup converter, whatever may be this DC to DC single quadrant converters? How to find out the relationship between input voltage and output voltage?
Voltage balance.
Okay, we have to make the, here we are having the inductance in the filter side. Okay, we are having a inductors at the filter side, and volt second balance. Volt second balance. What is the voltage when switch is on across the inductor? What is the voltage when the switch is on, and what is the voltage across the inductor when the switch is off? And we get a volt second balance. Voltage multiplied by duration. What is the inductor voltage during on time and during the off time? And our volt second balance, our total average voltage, in other words, we can call as the average voltage across the inductor should be 0 over a cycle time. Basic for finding out the relationship between input voltage and output voltage. of any DC to DC converter. Our theme is average voltage across the inductor over a one cycle time, that will be 0. And here one cycle time corresponds to a duration of on time plus the duration of off time, T period. Now let us assume how will be the circuit, how will be our circuit when our switch is on. Let us assume that when the switch is on, so what we say that our VD, this switch is on. Let us assume that the switch is on. So when the switch is on, this will be connected to this. Okay. And we have seen that what will happen to a diode. Here you will see that our diode will be open circuited here because this is a positive voltage. So diode will become off here. When the switch is on, we can say that a diode will off here. So we can remove the diode. We remove the diode here, diode, and then remaining circuit will be a VD. What we are having VD, then LF, C, and VO. And this is the position we have shown it here when the switch is closed. When the switch is closed, we have seen that VD is connected to the inductor, and one side of inductor, if you see it here, this will be a voltage is VD. Other side, we have seen that our output voltage under steady state output voltage for a particular duty cycle, output voltage is constant VO. So we represent the VO. So one side of inductor, if you take this as a common, one side of the inductor we are in plus VD, other side of the inductor is having a plus VO. And what is the voltage across the inductor? With this polarity we represent VL as this, and VL will be now VD minus VO. VL will be a VD minus VO. Is it clear? So this will be our water voltage across the inductor. This will be a VL voltage across the inductor will be a VD is the input voltage minus the VO. And here we have seen that the VL will be positive or negative. Here VL will be a positive or negative. VL will be VD minus VO. Our converter is a buck converter. Our converter is buck converter. So VO is less than VD. So VL will comes out to be a positive, is it right? VL voltage, here it will be a positive polarity. We can call it with shown this. Our VD is more as compared to VO. So the voltage across inductor value will be a VD minus VO, and magnitude will be a VD minus VO, and a particularly polarity will be a positive voltage. Now let us consider another case when the switch is open. When the switch is open, we have shown the open switch here. And now whenever switch is open, now we have seen that when the switch is closed, our current will be flowing like this. Current will be flowing like this when the switch is on. And inductor is stores the energy. Inductor stores the energy. When the switch is open, then what will happen? We should require a path for the inductor energy. So current, inductor current will be making a path through this capacitor and load and through this. So diode will be a conducting here. And when diode is conducting, we have seen that our load, capacitor, and this inductor, they will come in parallel. And our voltage across the inductor will be a minus VO. Why we are calling minus VO? This particular terminal we assume as a reference positive particularly. And now this will become positive here, and that's why we can call as a VL will be a minus VO. So we have seen that when the switch is on, voltage across inductor is positive value, and when the switch is off, voltage across the inductor is VO. How much duration this VO will present? VO will be for a period of T off. How much duration our switch is off? So VO will be minus VO will be for the duration of T off. And how much duration this it will be period of T on. So this will be for a period of T on. How much duration the switch is on. So now what will be our average voltage or the volt second area? This is a VO minus VD minus VO multiplied by T on. That will be positive volt second area, and minus VO into T off, or VO into T off, that will be a negative volt second area. And now we can have a average voltage is 0. It means that a positive volt second area will be equal to negative volt second area. Okay, so our positive volt second area, we have shown it here, particularly our positive volt second area. So this is our positive volt second area, Vd minus Vo into T on. That will be our positive volt second area. This will be represented as the A. If you see it here, this will be the area A. That will be a positive volt second area, and Vo minus T off. This period is T off, and Vo minus T off is the negative volt second area. And these two areas should be equal, so that average voltage across the inductor will be 0. In case of DC circuit, average voltage across the inductor will be 0. And this is the waveform you are seeing across the, this is the waveform across the inductor. Inductor will have a positive voltage when the switch is on, negative voltage when the switch is off. And now when the switch is on, our current will be goes on increasing. We are assuming our current will be a continuous one. So current will be a goes on increasing when the switch is on. Current goes on increasing when the switch is on. Okay, and when the switch offs, when the switch become off, uh, current will free will through this inductor, current will goes on decreasing and free will through this. So current will goes on decreasing. Again switch on, current will be goes on. This is we have shown for a continuous conduction. What is meant by continuous conduction? Our inductor current is the continuous. Our interest is to get the relationship between, in case of any DC to DC converter, we are using the concept is volt second area, positive volt second area across the inductor, that will be equal to negative volt second area. And you just simplify this, our output voltage, particularly we are getting VO is the output voltage, will be input voltage into T on by T, T on by T, and this T on by T, this ratio we can call as a D. So here if you see that the output voltage will be a input voltage multiplied by duty ratio. And what is the range of duty ratio? What is the range of duty ratio? In which range we can vary the duty ratio? What is the range for variation of D? Duty ratio of any chopper circuit or any converter. What should be D? D will be given by T on by T. Our
0
T
to
on
1.
may be 0 or T on may be equal to T. So D will be, what is the value of D duty ratio? It will be between from 0 to
1.
1. So duty ratio will be a 0 to 1. It means that our output voltage will be maximum equal to input voltage. We can get the output voltage minimum 0 to the input voltage. We cannot get the voltage above the input voltage. And that is why we can call it as a buck converter. Our interest is we want to make the circuit compact. We want to make the circuit compact. We want to reduce the size of the circuit. So how we reduce the size of circuit? Any idea? Suppose we want to reduce the size of circuit. We make this circuit compact. How we can do that? Any idea? Any your any comments? We want to make the circuit compact. What is mean by compact? We make the circuit physically having a smaller size, that we can call as a compact. So how we make the circuit compact? Any idea how to make the circuit compact? Any option is available or not? This is the part. Except load, this will be our converter. In this, our converter will be this part. Okay. If this is a converter, again input voltage is not a part, output. So our part of converter, this is the part of converter. What comes under the converter? How many components are coming under the converter? These are the components coming under the converter. What are these components? One is a switch, other is diode, third is inductor, and fourth is the capacitor. These are the parts of the a particular our power components of the DC to DC converter, and there will be a control circuit will be there. So how to make it compact? We want to use the small values of LF and CF. Our interest is we want to go for a small values of LF. So how we make the circuit compact? How we make the circuit compact, and we have to use a lower values of this L and C. And for getting the lower values of L and C, we want to operate this particular chopper at a high frequency. Okay. So how to reduce? We want to make it compact. We want to make it compact means we want to reduce these passive components L and C. And how to reduce the L and C? One option available is to increase the switching frequency of the chopper. We want to increase the switching frequency of the chopper. If you increase the switching frequency, definitely LF and CF, that values will be reduced. We can refer any text. We are not given derivation of this, but these values will depend upon the switching frequency of the chopper or the DC to DC converter. And so one option is we have to make the circuit compact. It is nothing but we have to increase the power density of converter. It is same, is it right? We make the circuit compact. It means that we increase the power density of the converter. And how to get the power density, higher power density? We want to reduce the size of the physical components, that is L and C. And how to reduce the L and C values? Option available is to increase the switching frequency of the chopper. We have to operate at, so output voltage is not depend upon switching frequency. So which parameter governs the output voltage of this converter, DC to DC converter? Which parameter controls the output voltage? Is it a switching frequency or duty ratio?
Duty ratio.
Duty ratio will control the output voltage. So we can control the output voltage by controlling the duty ratio. And our interest of the switching frequency is we can maximize the switching frequency. We can operate this at a maximum switching frequency so that our values of L and C will become a smaller one. Now, what will be the problem if you go for high switching frequency? Is there any problem? If you go for, if you suppose I increase the switching frequency so that I will get the less values of L and C, then is there any problem with the high switching frequency? Is it a problem with high switching frequency?
Yes, sir. The value of L and C depend upon switching frequency.
Okay, so to reduce that values, we increase the switching frequency. Okay, so that the values of L and C will reduce. But we can get something, and there will be definitely some loss will be there. We cannot get everything. Okay, for getting something, we have to lose something. So here we reduce the values of L and C. Then what will be our problem then?
Losses will increase.
Okay, then our will have a switching losses will increase. So we want to try to make the circuit compact. It results into a compact circuit, but losses will increase. So efficiency will decrease. And now our interest is we want to improve the efficiency. We want to improve the efficiency. And for improving the efficiency, we want to reduce the switching losses. Improve the efficiency, we want to reduce the switching losses. And this is one of the approach, resonant converters, where we reduce the switching losses. In the resonant converters, we are having various techniques to reduce the switching losses so that we can make the circuit compact. At the same time, efficiency of that circuit will be high. So here, so we are calling about why we can operate the any converter. Converter means any DC to DC converter, particularly at high switching frequency. What are advantages? The first advantage we have discussed is a size of passive components. And normally in case of DC to DC converter, we are having two major passive components is inductors and capacitors. There will be a passive components, and okay, so we reduce the size, and they are having a maximum weight, so we can reduce the weight. And as size is reduced, definitely we increase the power density, and then cost of the converter can be decreased because value of L and C required, that will be reduced. Cost of L and C will be reduced, and definitely the cost of converter will be reduced. But if you go for high switching frequency, then what is the drawback associated with this? When you go for high switching frequency, drawback will be a switching losses will be a increased. Okay, and because of that, converter efficiency will decrease. Here, whatever we are discussing, we are up till now we are discussed second year power electronics we discuss, and in that case we discuss the choppers or this DC to DC converters, inverters in the second year power electronics. And earlier this we have discussed the two modules. We discussed the PWM rectifiers, PWM converters, multi-level inverters. In all these, whatever switching of devices we are doing, that switching of devices we can call as the hard switching. Okay, that device we can call as the hard switching. Okay, and now we are going to discuss here. We have taken the example of a particularly a two-level inverter. Okay, so many times we are discussing the two-level inverters. The two-level inverter, 6 devices, DC voltage, LC filter, load, all this we are discussed. And here we have just shown one leg of this. Okay, convention here and here is different. We are taken from this. Input voltage is here we are calling as a VD throughout this, but our earlier we are referring as the VDC. So let us, okay, some convention you follow. So we follow this. This is the VD, is the DC link voltage. We represent the switch here. Okay, one leg we have taken. T plus T minus you can call as S1 and S4. D plus and D minus, that is a D1 and D4. Okay, we have just taken the particularly this, and we have seen that this current IO will have a two direction. This is a one direction, and another direction of IO will be this. Okay, opposite to that. So here in case of this is a VSI, is it right? This our particularly this converter or this particularly inverter we can call as a VSI, voltage source inverter, particularly VSI. And in case of this VSI, we have shown that our DC voltage polarity is fixed. Okay, upper is positive, lower is negative. Is it right? This is upper is positive and lower is negative. So this DC voltage polarity is fixed. But whatever our DC link current, our devices, if you now make it, our IGBT is a unidirectional. Anti-parallel to that, diode is a unidirectional, but diode is carrying current in one direction and IGBT is carrying current in another direction. So this IGBT is carrying current in downward direction. Okay, let us assume here this will be IGBT is carrying current in the downward direction, whereas diode is carrying current in the upward direction. Okay, diode is carrying current upward direction. So here what we say, each now device IGBT with anti-parallel diode will now become bidirectional device. Current can flow, combination of that current can flow both directions. It means that individual device is unidirectional. Current in the IGBT will flow in downward direction. Current will flow in diode in the upward direction. And because of that, our DC link current, what is this ID you can call it? This current we are having either this direction or this current, we can have a this direction. Okay, so DC link current can be either positive or negative. DC link current can vary, and based on that, we have seen this will be our quadrant operation of this inverter. Inverter will always work in the two quadrant. VSI. This is the quadrant operation of the VSI, where it works in the first quadrant and the second quadrant, assuming our ID will be the x-axis. Okay, ID will be the x-axis. So this is the quadrant one, you can call it, where power is flowing from DC side to AC side for inverter. In the second quadrant, we can say that power is flowing from the AC side to the DC side. So this is the two quadrant operation. And now whatever switching we are getting up till now, that switching we can call as a hard switching. Okay, why we are calling it hard switching, we'll discuss this. So this particular switching you can call as the hard switching. So up till now, whatever we have done, power electronics, choppers and inverters, we have done it. Similarly, PWM rectifiers, multi-level inverters, where we can say switching is the hard switching. Switching is the hard switching. It with that conventional switching, we are not doing anything special. We are just give the input to the signal when you want to on it, and if you want to turn off, you give the signal for turn off, because these devices are fully controlled devices. Is it right? If you want to turn on, we apply a positive gate signal, maintain positive gate signal. If you want turn off, you apply the negative or zero gate signal. So we are not bothered about anything about the what is voltage across switch and current to the switch. When we require to turn on, we turn on it. When you require to turn off, we require to turn it off. But while switching, if you see it here, this we have shown it here. Let us consider this diagram particularly. Let us assume that first is our switch is off. You take any switch. So here this instant you see here, so up to earlier to this, okay, earlier to this, what we say it here, what we say here is this is the waveform what I am calling voltage across the switch. Water waveform I am drawing here. Okay, this is the voltage across the switch. So here voltage across switch, if you see it here, is 0. And now if you go for a current through the switch, this is the current through the switch. So earlier up to this vertical line, what is our switch position? Let us assume that this is the switch. So what we say it here, voltage across the switch is 0 and it carries current. So this is we can say the switch is on here. This period is earlier to this, the switch is on. Okay, we take our switch is on earlier to this. Now at this instant, we apply the signal for turn up. We make the gate current or gate pulse, gate voltage or gate to cathode or gate to source voltage, we make it 0 or minus. And now at this instant, whatever I am showing it here, at this instant, we apply the signal to turn off. We apply signal to turn off. But due to semiconductor physics, what happens? Here, as we apply the voltage for turn off, the voltage across the switch will increase. This is the voltage across the switch will increase. Okay? But current will not decrease. The current will remain same. And when voltage reaches to a full value, then current, after that current start decreasing. This is because of all is happening because of semiconductor of physics. Is it right? Because of the semiconductor physics. So here what happens? So when you give the signal to turn off, we have seen that our current is not becoming zero. Our current is not becoming zero, but voltage will goes on increasing because the device is on, voltage across it was 0. Give the signal, the voltage across it will goes on increasing, but current will remain same as it is. So during this period, during this period. Now current, if you see it here, so this will be our, what we are having is this will be current through the switch and the voltage across the switch. Both are there. So simultaneously it will be present here. During this period, if you see here, this is the period where you can call as turn off period. If you just look at this instant, a turn off period, we initiate the signal. Here, device starts turn off. How it turns off? By increasing the voltage across the device increases. When voltage reaches to a rated value, then current will start decreasing and then current will become off. And this is a turn off period. Turn off period is few microseconds. Okay, depending upon the device, the turn off time is few microseconds. But during turn off time, we have seen that voltage across the switch is present and current across the switch is present. So simple, we can get it voltage multiplied by current. We take a simple voltage multiplied by current, and that is nothing but this particular triangular type area. This particular triangular type area, what we are getting, this will be a product of VTIT, and this is the power loss. This will be the a power loss taking place. And reason is because when turn off takes place, what is happening? When turn off takes place, our current is not becoming zero, but voltage will increase. And after achieving the rated voltage across the switch, then current start decreasing. So here at one instant, we can say that voltage across the switch is maximum and current through the switch is also maximum. And this particular switching we can call as the hard switching. And because of that, this area under curve, P into T, that will be energy loss. This will be energy loss taking place during the turn off. This will be energy loss taking place during the turn off. Okay, so power is not a constant, but power is in triangular shape. VTIT divided by 2, whatever we are having, that will be the energy loss taking place. So now our device is off. This will be our device is off. Okay, this will be off. Once it is off, no switching loss. Okay, now we want to turn it on. Now we turn it on. Again, here at this instant, we initiated the turn on process. At this instant, we initiated the turn on process. But while doing turn on, first current will increase. That is the, okay, first current will increase, reach to a rated value. And after reaching the current to the rated value, then voltage will decrease. So here voltage will decrease after this. And again here we have seen that turn on period. Both voltages and current across the switch are present simultaneously. And because of that, loss is taking place. And that loss we can call as a switching loss, turn on loss and the turn off loss. Okay, and this, what is the reason? Reason is because of the semiconductor physics of this. Okay, and because of that, loss is taking place. And this is the area, whatever we are having a energy, what we are in P into T. This is the energy per switching we are having. This energy per switching is now fixed. And if number of switchings are more, definitely energy will be more, and it means that power loss will be more. So what we say, what is the relationship between switching frequency and turn on and turn off loss? Or switching power loss is directly proportional to. So this switching power loss, we can call it this is a switching power loss. We can say it is directly proportional to, okay, directly proportional to switching frequency. You can call as Fs. Okay, I will say it will be the Fs. So switching power loss, that is directly proportional to the switching frequency. And as switching frequency increases, definitely the switching loss that will be taking place. So this is the reason. When this is, we are not doing anything. When we want to turn on the switch, we turn on it. When we want to turn it off, we turn it off. And that particular we have done in all our PWM rectifiers, PWM inverters up till now. And this is what we can call as hard switching of the converter, or a PWM converter and the PWM inverter. That we can call as the hard switching of the devices. Any question? Is it clear? So this is because of semiconductor physics. We can say that during turn off, what has to be happen? Okay, current has to become zero, but reverse is happening. Voltage will increase, and after that, current will be goes on decrease. This is happening during turn off. During turn on, current will increase first, and then voltage will decrease. Okay, and because of that, simultaneously across the device, current through the device will be more, also voltage across the device will be there, and because of that, power loss is taking place. That power loss area, what we are having, it will be a triangular in fashion. Okay, this will be loss energy, you can call it switching loss energy. Per switching we are getting, and if switching frequency is more, switching loss energy is more, it means that the switching losses will be more, and switching losses will be proportional to the switching frequency. Now our interest, how to reduce this? Is it right? We want to reduce the switching losses. What will be a concept we can use? Or before going to that, okay, so whenever this taking place, if you see it here, okay, we take our device is on. Device is on. What is the voltage? Voltage will be a 0, and current will be maximum. So if you want our VD, see our voltage across the switch, VT, we can call it. And here VT, now voltage is 0 and current is maximum. Voltage is 0. Our x-axis is the voltage, y-axis is the current. And if you see here, particularly when the device is on, we have seen that our voltage across it will be 0 and current. So this will be a point we can represent here. Our switch is on. This is the point where we can represent the switch is on. Whereas another here, if you go here, whenever our switch is off, when the switch is off, if you take this case, when the switch is off, a current will be 0 and voltage will be rated. When the switch is off, here we see the voltage will be higher and current will be a 0. So this is off, and now our device will become on to off or off to on. And while during this instantaneously, this is the trajectory we are following. Suppose the device is off, so it will be becoming on, and instantaneous values of voltage and current across the switch. This is the trajectory I am showing. That will be instantaneous voltage. That is during this period. Whatever this we are represented, whatever this. So how the voltage across the switch during the turning off or during the turn on, how it follows the path. Okay, so it is off instant. If you want to turn on, we have seen that initially voltage will increase. If you want to make it on, initially current will increase and then voltage will goes on decreasing. This is the case for turn on. While in case of turn off, what happens? In case of turn off, particularly our voltage will increase. This will be x-axis, voltage will increase and then current will decrease. And so that this is what we can call as a switching trajectory. Instantaneous voltage and current across the device during the transition from on to off or off to on. Okay, so here we mark the instances on here. So transition may be from on to off or off to on. And this is the what we can call it an area under this trajectory. Also another way we can say that the area under this trajectory, area under whatever this area coming under this trajectory, you can call as a switching loss. Okay, yeah, this trajectory or area under this trajectory will be proportional to the loss. If the area is more, definitely switching loss will be more. Area is less, the switching loss will be less. And now this trajectory, voltage across the switch and current through the switch during turn on and turn off, that should be within the safe operating area of the device. So every device manufacturer will provide how much will be the voltage, and particularly IGBT, we have seen that this area is a particularly the rectangular area we are having this, and whatever the switching trajectory, it should be within the safe operating area. Turn on and turn off, that switching trajectory, turn on and turn off, that switching trajectory should be within the safe operating area. It means that whatever this particular trajectory, in other words, it represents the voltage and current rating of the device. Voltage and current rating of the device. So we see that what is the maximum voltage, and definitely our the switching transients on to off and off to on, that should be within the safe operating area. And particularly for IGBT, this area will be somewhat, we are in a square or rectangular area we are having. So we are not normally using the snubber circuit. Okay, thyristor we are using the snubber circuit, but particularly MOSFET and IGBT, we are not using the snubber circuit. So what is the importance of safe operating area? This switching trajectory of voltage and current during turn on and turn off, that should be within the safe operating area, so that a life of the device will be assured. So that device will not damage. That is what we can say, that whenever turn on and turn off trajectory is within the safe operating area. And the area under this whatever hatched area, that will represent the switching loss. So is it clear how the why the switching loss is taking place during turn off and during turn on, and how to compute that instantaneous voltage and current across the device during turn on and turn off, that particular represent the switching loss. And we can have a hard switching trajectory, how the voltage and current instantaneously changes during the turn off time and the turn on time, and area under this curve will represent the switching loss. Any doubts?
No, sir.
Now let us go for, so this is what we are having. Now we have discussed the hard switching. Okay, one drawback is the losses will increase. That will be a one drawback we are having. And what will be other? So we have discussed this particular point. We have discussed this is the switching loss, switching power, high switching power loss will take place. That is a one drawback we have discussed. But other drawbacks are also there. Entire load current is turn on and turn off, entire load current during the each switch, that will be, we require a switch rating. Here high switching trace you can call it, voltage across the switch is changing very fast, current through it will be changing very fast, and because of that our we are di by dt and dv by dt, that will be a more, okay, because of changing. And because of that electromagnetic interference will be also present. So these are the drawbacks of particularly hard switching. And we have seen that switches are subjected to a high switching stress. They have to either turn on and turn off entire load current or voltage. Switching loss will be there. Here our di by dt is high, our dv by dt is also high, and because of that we are having a electromagnetic interference. Now how to reduce this? Okay, now our question is how to reduce this. We are having various options for that. How we reduce the turn on and the turn off loss. Any questions?
No, sir.
So now, okay, we have to discuss few things. Okay, without this, so what we discussed today. Okay, we are having almost 32 and others. So see, how many people are present at present now? How many you can see? Total numbers.
39.
39. Okay, 39 people are present. Okay, fine. So what we discussed today, is it correct? So our interest is, so why we are going for resonant converter? Okay, we discuss half an hour we are discussing. So why we are going for this topology of the converter? Resonant converter is again one type of converters we are having. So why we are going for this converters? Anybody? Why we are going for this type of converter? What is the motivation to go for this converter? Roll number 15, Akash. Row 15, can you
May-
answer this?
Sir, device compact.
Oh, we are discussing about the converter, not device. Okay, device means our IGBT MOSFET that will be coming under your semiconductor physics area and okay, semiconductor technology. Our interest is we have to making some device. Device means we are making some converter, inverter, is it right? Or a chopper, and that circuit we want to make a compact. Why we have to make compact? Okay, we want to be reduced size. Always we want to be in the form of miniature circuit. We want to be a miniature circuit. Okay, making the compact. You are seeing that size of each and everything is reducing. Earlier, we have seen that our computer, if you go for 1950 or 1960, our computer is having one room. Now we are having a computer in your, okay, mobile is a computer and that will coming very compact size. Okay, so that is how we are going for compact. Okay, so we want to make the size so that cost will reduce, performance is to be increased. So our interest is we have to reduce the cost. Everything we are making economical one. We want to reduce the cost. At the same time, we make the equipment compact. And for that, we want to go for a how to make the converter compact, particular DC-DC converter, by reducing the size of L and C values. And for reducing L and C values, our option is if you go, we have to operate the converter at high switching frequency. And if you operate the converter at high switching frequency, we are having a problem of losses. And now our interest is we want to reduce the losses by not hard switching, but we are making it a soft switching. And what is mean by the soft switching of the particular these switches or soft switching of the converter, that we can discuss. And the soft switching of the converter, another name is nothing but the resonant converter. Soft switch converter is nothing but the resonant converters. So now any question? I think with this you are, at least you should have some doubt in your mind, or you don't have any doubt. At least you should have some doubts. Is it you understood or not understood at all?
Yeah, understood.
Any question? I am expecting at least one question from the audience. So you have to raise the question. That is very, very important. Is that will be a best learning to the teacher. When teacher learns, only if student ask questions. Is it right? If you ask question, that is not for you. This is for the teacher. You can take it. Is it right? If you ask questions, definitely teacher will think on that and he will learn. Okay. So asking question is better for better learning of teacher. At the same time, better understanding of the student. So very, very important, you should ask the questions. I will appreciate, though you ask the wrong question, I will appreciate that. But you have to ask the questions. Make the habit. Okay. While studying also, you raise a, every time why. You raise the questions why we are doing this, why it is required. That will be the only way to understand the things more clearly. So you always you try to raise this. Okay. Hello, what is question? Di by dt once again? I have not seen the question. I just unmute and tell, ask question. Hello. I think I have just seen the question, but okay, very short duration was present on my screen. So what was question?
Sir, it is there in the chat box.
Okay, fine, fine. So anybody other has seen question? Can you just repeat that question? We'll try to answer.
Can you please explain how di by dt accounts for EMI?
Okay, so you have seen that. Okay, I am going giving a very layman person answer. Have you seen aerial or any conductor is acting as an antenna? If you have seen that, okay, if you are listening radio with mobile, is it right? And any conductor, you are connecting just the wire, is it right? Headphone wire, that will be a particularly. So any conductor is working as a antenna, you can, it emits this. And if di by dt is there, definitely it will emit the radiations. Okay, and that we can say in other words. So whenever di by dt is high or dB by dt is high, definitely it will radiate the signals. And that we can call as a electromagnetic interference. I think is it okay? So whenever we are having a okay, current is always associated with magnetic field. You are knowing it, but whenever high di by dt or high dV by dt, definitely it will have a our a particularly conductor itself will work like a antenna and it radiates this electromagnetic interference. Waves it will be there, or you can call it as a signal, and that will be definitely we can call as a electromagnetic interference. Is it okay? So we meet. Okay, so we meet tomorrow at the same time. Okay, thank you.